As well. It's a real honor and a pleasure to be in Ukraine today. We're going to talk about Kubernetes and gRPC. Some of these things may not be very familiar to you. So if you have questions, we'll try and do a Q&A session afterwards, but you can find me around the conference for the next 2 days and ask me questions, or you can tweet me questions at any time. So we're going to be talking about scalable microservices with gRPC, Kubernetes, and containers. And this is me, Mandy Waite. I'm a developer advocate. I work for Google. I've been working for Google for 5 years. Developer advocate means I work with developers to get the best possible experience from the platform, the Google Cloud Platform, for those developers. You can get me on +Mandy Waite on Google+, or @TechGirl on Twitter. And down here, you'll find on every single slide, it's got my Twitter handle. So if you want to tweet me with a question, please feel free to do so. So we're going to start off with my normal kind of introduction to Kubernetes, because it's quite a difficult subject to get your head around. So what is this? What are we looking at here in this picture? So this is a Google data center. This is a data center in Iowa in the US, a place called Council Bluffs. And this is one of our bigger data centers. We have lots and lots of machines, racks and racks of machines and cooling and such like. But the important thing here is that how do our engineers use something like this data center? We don't really want them to have to worry about locating a machine within a rack within a data center, and then SSH into that machine, SFTP in a binary over, standing up their binary, the thing they want to run, maybe doing that many, many times. We need to make it much more easier for them to actually make use of this infrastructure when they're doing development. So how do we do that? And we do that through something called Borg. How many of you have heard of Borg? Right, Valentine has. So Borg is our internal cluster scheduler. It's the thing that our engineers use to run programs. And basically what they do is they create a configuration file. They create a binary as well. They have to run the binary. But they create a configuration file that looks like this. We have a job. We have hello world. That's the name of the job. We have a cell. The cluster we saw, well, the data center we saw previously on the previous slide is what's called a cluster. And within clusters, we have cells. And cells are typically 10,000 machines or so. So in this case, we're specifying which cell we want to run the job in. We're saying what the binary is, and the binary is a statically linked binary. This is a hello world for the data center application, and it includes its own web server, so everything's all linked inside the binary. It also will run ultimately in a container, a very lightweight container that we use internally at Google. They can specify ports. In this case, it's a web server, so we have to specify the port name, a number. Requirements. How much RAM do we think it's going to need? How much disk do we think it's going to need? How much CPU do we think it's going to need? And finally, how many copies of this job do we want to run? How many tasks do we want to run? We can say 5, but because this is Google, maybe 10,000 is better. And 10,000 is a perfectly reasonable number to run on our Google infrastructure. So this is what the developer specifies, and ultimately he will, or she will, submit a job to Borg using a configuration utility on the command line. So I'll just say Borg CFG, pass in the name of the configuration file, and it will be sent off to Borg, and it will handle the process of scheduling that job for them. And ultimately, after about 2 minutes, 40 seconds, we have 10,000 tasks running. 10,000 instances of that job will be running. It takes a little while to ramp up. We ramp up slowly. There's no need to run these things immediately. The binary itself is probably around 50 megabytes in size. And so there's quite a significant amount of data to move around between those 10,000 machines that are actually running this job. So we ramp it up slowly, and at 2 minutes, 40 seconds, we get to a point where we have 10,000 running. And what actually just happens when the engineer submits he or she's configuration file is this. So the binary has been built already. They built this using our massively distributed parallel build system called, well, I can't say what it's called, but it's available externally called Bazel on GitHub, B-A-Z-E-L. They build the binary. The binary is pushed out into local storage for the cell. Then they push out the configuration file, and that gets sent to what's known as the Borg master. Now, the Borg master sits within the cell. It's replicated 5 times for resiliency, and the configuration file is stored in persistent storage. That's Paxos-based, consensus-based storage. And at some point, a thing called a scheduler comes along and says, what's the state of the system and what should the state of the system be? And it will see there's 10,000 new tasks to be run. And it will say, I should be running these. I'll run them. So it fixes that. It starts trying to run those 10,000 jobs. It comes up with an execution plan where it's going to run them. Then it talks to potentially 10,000 machines to say, I want each of you to run this job for me. And it will send a signal to the machines, and these are the machines down here. These are nodes within our cluster. And they will go and retrieve from self-storage the binary to run. And they will then start running that task. So at the end of it, we have a situation where we have 10,000 Hello World tasks running on our data center. That's the way it works. And that's what we do at Google. Now, the whole idea of Kubernetes, which we're going to talk about shortly, is to make that possible for everybody else to do as well. So we've learned huge lessons over the last 15 years or so when it comes to scheduling binaries. And Kubernetes is an attempt by us to make that possible for everybody to do. And we'll talk about how that works now. How many of you are familiar with Docker? Oh, not so many of you. Oh, okay, that's kind of worrying. Right, so Docker and containers are extremely important. I'm not going to go into details about containers today, because otherwise the talk would be kind of bogged down by talking about what containers are fundamentally. But containers basically are lightweight versions of a virtual machine, kind of like a virtual machine, that are very easy to run, and very portable and very repeatable. They're very easy to build. You create an image. Once you've created the image, you can create a container from that, and then you can run it and schedule it wherever you want to. So once you have the container, you can push it out to a scheduler like Borg, and it will run it for you. That could be on your local machine. It could be on a cluster. So that's what containers are. Containers generally, as people have been finding out, make people more productive, make developers more productive. And everything at Google runs in a container. Ultimately, from what we've just seen, is the data center is one big system on which we run containers. And if you want to find out more about scheduling and about containers generally, there's a link to a video of one of my other talks where I go into it in more detail. So these slides are available online. You have the link at the end. So let's talk about Kubernetes. Kubernetes is a strange word. It's difficult for many people to say, difficult for everybody to say, pretty much. So if you're interested in finding out how to say it later, I'll be outside and I'll help you. But it's Kubernetes. It's a Greek word. I'm not going to get into the details of that. But ultimately, what it does is an orchestrator for containers, for Docker containers, for eventually for any type of container, once we have a standard in place. And we're working on a standard currently. It supports multiple cloud environments. So we have many, many different people working on this. It's not just Google. You can run this stuff on Amazon. You can run it on Microsoft. Red Hat OpenShift is built on top of Kubernetes. Mesosphere use Kubernetes. CoreOS runs Kubernetes. VMware use Kubernetes. So many, many people were actually using Kubernetes and actually contributing to it. It's an open source project, as we'll see later. It's written in Go, and ultimately, it's inspired and informed by everything we've ever done in the last 15 years when it came to building Borg. Because Borg is like a house, a very old house which you've built extensions on over time, many, many different extensions. And while the house is functional and does what it needs to do, you'd probably want to start off again at some point and rebuild it completely with all of those extensions built into it. So Kubernetes is like a fresh start. We can now build functionality that we know we would need, but that we didn't have initially in Borg and we had to add on afterwards. So ultimately, Kubernetes will be better than Borg. And ultimately, as well, the goal is to manage applications, not machines. DevOps people, as we'll see shortly, can manage all of your clusters for you, but ultimately this will leave developers free to actually develop applications and not have to worry about infrastructure. Kubernetes looks kind of similar to what we saw with Borg. We have a Kubernetes master, and we have a bunch of nodes at the bottom here. We have an API, we have a scheduler for scheduling work, and we have a thing called a kubelet running on each of the nodes. We will manage the work that runs on each of those nodes. We also have a registry for images, images that we want to build containers from. And this effectively serves the purpose of the cell-level storage we saw previously. So, let's get into the nitty-gritty of Kubernetes. So containers are kind of strange in the way they do things, and pods in Kubernetes are a kind of level of abstraction that's a little bit different from a container. So a pod is like a host machine, but a host machine that you can schedule on a cluster, or something can schedule for you. You don't really want to schedule it yourself. You'll have something else scheduling it. And that means we can run containers on that pod, that logical host, that can talk to each other like they were running on the same machine. In this case, they are running on the same machine, they run inside a pod, but we've simplified the container abstraction that Docker provides. And a pod effectively hosts containers and volumes, and also it has its own IP address. So each pod will have a routable or routable IP address, not NAT. Pods are things that come into existence when they're needed. These are scheduled by the scheduler. They may go away, they may come back, and ultimately they're ephemeral. Functionally identical, every one of them looks exactly the same, and so they're therefore ephemeral and replaceable. You can actually group containers within a pod. So when it makes sense to have two things running on the same machine, you can have the two things running in a pod. In this case, we have an example where we have a Node.js application that's serving client traffic, standard web application pretty much. And we have something that's synchronizing with Git, with a GitHub repo or a Git repository, and looking for changes in that Git repo, pushing them out to a shared volume within the pod, which will then be picked up by the Node.js application container and scheduled and pushed out to consumers. So containers effectively are tightly coupled. It makes sense for them to live together, but it doesn't make sense for them to live on their own. So when the pod goes away, both of the containers go away in this case, it could be more containers, and the volume goes away as well. Pods have shared namespaces. They can talk to each other as if they're running on the same host, in terms of both network traffic and also port namespaces, and also RPC. Networking looks like this. So again, if you're familiar with Docker, you're familiar with the Docker networking model. This is a little bit different. In order to make this work, we need some additional functionality. And in the case of Google Cloud Platform, we provide that through Google Container Engine and Google Compute Engine. But ultimately, a pod, the blue boxes are nodes here. The nodes actually running pods. The green boxes are pods. And the pods can talk to each other directly via their own IP addresses. So the IP address that a pod sees of its own is the same IP address everybody else sees of it. That's a little bit different from what Docker does. Ultimately, if you want to do this on something other than Google Container Engine, Google Cloud Platform, you'll probably need some network overlay, something like Flannel or Weave or some other cloud provider. I think Amazon also provide it as well. Ultimately, when it comes to grouping mechanisms within Kubernetes, we have one thing, and that's called labels. Everything can be labeled within Kubernetes, and we can group anything with a label into other services, replication controllers, custom applications that you build yourself. So in this case, we have a pod with a label. The label is type equals FE in this state. This is completely arbitrary. It's a key value pair. It means something to you, it has semantic meaning to you, but it means absolutely nothing to Kubernetes, apart from being as a grouping mechanism. And ultimately, you can build dashboards around labels that will consume pods and other artifacts with labels and show the state of those labeled objects within a dashboard, or maybe just a shell script. And you can build other dashboards that look at different things, different labels within the system. So in this case, we have type equals FE as a label, we have version equals V2, and we have 2 different dashboards looking at those labels. The next thing is replication controllers. So now we've mentioned pods, and we've also mentioned the scheduler within Borg and within Kubernetes. And really, this comes down to something called desired state. When we deployed the application at the beginning, we said we want 10,000 of these. This is the binary, these are the details, this is the number we want. So that's a template for creating effectively pods or running processes. And the replication controller's responsibility is effectively to create pods based on our specification. And that will be a template for creating containers and pods, and also the number of replicas we want. Is it 5? Is it 10,000? Or in this case, 2 as in the diagram. So the replication controller effectively makes sure there's always 2, in this case, 2 of these pods with label equals version equals V1 running all of the time. We can create another replication controller that can manage pods with a different label. So in this case, we have a pod with label version equals V2. And that's managed by a completely separate replication controller. Then we have the notion of services. A service is another abstraction. So we run these pods. We don't know where they're running. So we could have a 100-node cluster with Kubernetes. And the pods could be scheduled anywhere within that cluster. We don't know where they are. So how do we find them? How do we actually get traffic to them and get responses back from them? We do that with a service. And a service, again, is a logical grouping of pods based on a label. So we have a selector that selects pods based on their label type, and they become the constituency of a service. The service provides a virtual IP address and also a DNS name, a DNS address locally that can be used locally. Then other services can discover that service and talk to it. We can also expose the virtual IP address externally as well to external clients. We'll see an example of that shortly. So ultimately, they get a stable virtual IP and port, and they also get a DNS name. Traffic that comes in from the clients is load balanced across the pods. This is done randomly currently. It used to be round robin, but now it's found it's better to do it randomly. But we do have session affinity based on client IP. So if we've had a request from a client previously, it will be routed to the same pod that processed that other request based on the client IP. So the developer view for Kubernetes looks very, very similar to what we had with Borg. We have a name, we have an image, which is our binary, effectively. We have resource limits, 128 megabytes, sorry, I always get that wrong. Half a CPU, we have our own special way of partitioning CPUs within Kubernetes. This is 500M, that means half a CPU. We can specify ports, protocols, and ultimately the number of copies we want to have. And we could replace that with 10,000 as well. So this is our spec, this is our desired state. Once we pass this through Kubernetes, it will create a replication controller for us that will keep this desired state. So ultimately, Kubernetes caters for ops and dev. In terms of ops, it makes it very, very easy to create infrastructure. Basically, you create a cluster, you deploy Kubernetes to the cluster, and then you don't have to worry about it anymore. You may add nodes or remove nodes to the cluster as needed, but the developer doesn't have to worry about that either. So this means the developer can just basically create these configuration files, create their Docker image, the container image, and ultimately not have to worry about where that will run within the cluster. So let's talk about HTTP2 and Protobufs. How many of you have heard of HTTP2? How many of you are using HTTP2? All right, okay, so it's fairly new, but there's some really good presentations out there. And I spoke to Ilya Grigorik recently and said, can I use your slides for my talk? And I did a talk on HTTP2 and gRPC recently in Amsterdam. That's online too. So some of these slides were Ilya's slides, which is why they're a little bit different from my own slides. So basically, HTTP 2 is designed to fix all of the problems of HTTP 1. That's pretty much it. Ultimately, improve end-user perceived latency, address many of those individual issues that HTTP 1 has given us. HTTP 1.1 has been fantastic, but it's taken time. Okay, you sure? Oh, okay. Oh, that's worrying. Okay. I have less time than I thought then. Okay. I'm going to rush on then. So HTTP 2 gives us this. Instead of actual slow perceived user latency when it comes to loading tiles, like in this image, we get very, very smooth loading of images. I'm not going to go into HTTP in very much detail, but there is a presentation online on our cloud platform site on SpeakerDeck, which will give you much more detail. But basically, it's based on streams. We have one TCP connection. Everything is binary encoded. We have a binary framing layer. We can do things like prioritization of streams. We can do flow control. We can also push things from the server to the client based on what the expected need is. And ultimately, we can compress headers as well. Protocol buffers are effectively something that we invented at Google very, very early on to improve communication internally. We had massive overhead. All of those machines have to talk to each other in some way. So we came up with the idea of protocol buffers to replace things like XML, other RPCs, so any kind of other standard transport mechanism. So we have about 48,000 message types, 12,000 what we call proto files. This has been an evolutionary development, so we've added to it over time, and we've incrementally solved problems with it. Today, we use it for RPCs, and we also use it for persistent data storage. So I'm going to skip over these, so you can read these in the slides, but there's various reasons why we think protocol buffers are good. This is a message format. This is what it looks like. It's strongly typed. This is protocol buffers 3, which is very new, replacing protocol buffers 2, which had things like optional and required fields. These things are also extensible, which makes it extremely useful. If you have an API that's defined within protocol buffers, you can extend it very easily without breaking the functionality of older clients that expect to have the older functionality. They will just ignore anything that you add to it. So you can find out more about protocol buffers here. gRPC is ultimately a service that's built on top of HTTP 2 and on top of protocol buffers to effectively give us an open source, standards-based, best-of-breed, and feature-rich RPC system that's much easier to use than the previous things we've had. It's efficient, idiomatic, and this is kind of like one line I kind of wrote to summarize what gRPC offers. Performant and scalable, and it's basically there for building microservices, and it can be used for building microservices on Kubernetes. So, again, Martin Fowler talked about microservices, and again, he knows them better than I do, so I'll leave it to him to explain them. And you've probably read what Martin's written about microservices, so I'm not going to go into them here. So gRPC ultimately provides us an interface definition language to describe an API, and it gives us tooling that we can use to generate servers and clients in 10 different languages, the 10 most popular languages. And this takes advantage of HTTP 2 even more than web browsers do. So this is built on top of HTTP 2 to specifically make use of HTTP 2 features. It ultimately supports unary connections, point to point, where we have one client, one message going from one server, or one server to one client, or vice versa. But also streaming. We can stream unidirectionally or bidirectionally. I should stop to drink some water. See, I'm rushing. Bidirectional streaming. So I'm going to skip over getting this started. In terms of language support currently, we have bindings for C++, Node.js, Python, Ruby, Objective-C, PHP and C, C#, and also with Java using Netty or OK HTTP. In-process is also there for testing. It also supports Go out of the box as well. So how much time we got left? 5? Okay. So I'm not going to talk about my microservice in too much detail because it's going to ruin the best part of the talk. So basically, we're going to have a demo application here that has a front end and a back end. And we have a replication controller for our front end and a replication controller for our back end. We have 2 services, one service managing the back end, one service for the front end. The front end one will expose an external load balancer, which will receive traffic from external clients. And I'm going to deploy that. And here is a visualization of what Kubernetes looks like. So what we have currently in the green box is a service. So this is a front-end service. I created this earlier because it uses a load balancer on Google Cloud Platform. And it takes a couple of minutes to create the external load balancer. And 2 minutes while you're waiting on a demo is a huge amount of time. So I created it earlier. And down here, we have a shell, which we're going to use to create more Kubernetes stuff. And so I'm going to use a tool called kubectl, which is part of Kubernetes. And it's very, very simple to use a configuration file to create controllers and services. So we have a YAML file specified in YAML called front-end controller YAML. And we deploy that. And that will create a front end for us. It stopped, unfortunately. And next thing I'm going to do is create a service. Oh, I've already created a service, right? Okay, let me create a service. So this is what it looks like. We have a replication controller, and we have 2 pods, which this replication controller manages. The 2 pods are part of the service. So any incoming requests will go to one of those pods. And we can check that out by opening that in a new tab. And at the moment, it's a very, very simple Hello World app. It doesn't do very much. So as microservices go, it doesn't do a huge amount at all. So what we can do is deploy a back-end service and a front-end service modification, an update, that will update what we have currently. So I'm going to deploy a back-end controller. It's going to get difficult to read, but now we have a back-end controller and 2 pods, which it manages. And now we're going to create a service which will be used internally by the front-end pods. Okay, so now we have 2 services, 2 replication controllers, and 4 pods. 2 back-end pods and 2 front-end pods. So the next thing we want to do is update that front-end controller, because it doesn't do very much currently. So for that, I'm going to do a rolling update. So this gives us the ability to actually update dynamically our pods, our deployed pods. So kubectl rolling update front-end, which is the name of the front-end controller we have currently. And we're going to update it with a different configuration file, and we're going to do it quite quickly. And what you'll see here is a new replication controller gets created, a new 2.0 pod gets created, then one of the 1.0 pods will go away. Now we have a 1 and a 2.0 pod. Then the final 2.0 pod will be created. It goes yellow because it's pending. It takes them a while to go from pending to running. And finally, the last pod will go, the 1.0 pod, and then the replication controller will be removed as well. And now we have a completely updated application. So if we go back to it now, we should see it looking a little bit different. So in this case, it's basically calculating the distance. This is a useful, a default distance between 2 points, latitude and longitude. So we specified the latitude and longitude, and you would have seen them on the slides earlier. And we measure the distance between those 2 points. And I can actually just do the last thing here, which is measure the distance between where I am now and where I'm going to be going tomorrow. So these are the latitude and long coordinates of here. Well, my hotel, 4924, and also where I'm going, which is Amsterdam. So 52.4. If we look at this, we'll see that's what we got here. Oh, I haven't specified the long too. Okay. Give me a second. Amsterdam is 4.8. Okay, so that's it. So it's 1,881 kilometers from where we are currently. All right, so I'm going to wrap up now. Sorry about that. And
okay, so we have questions, and if you wanna some of them, I can bring you a microphone and you can ask. So please stop your hand. Okay.
Hello, Mandy, again. I have a couple of questions. The first, it's Valentine.
yeah.
The first about gRPC and App Engine. Currently, there is no any opportunity to use gRPC in an App Engine. Is there any plans for that?
Well, I think gRPC is going to be there for managed VMs. So with managed VMs, you'll be able to use it straight out of the box.
Okay.
But using it in standard App Engine probably won't happen for a while. But we have some things that are coming along that may make it easier to use custom libraries like gRPC. Have you actually tried using gRPC with the Sandbox App Engine?
You mean a second version?
Sorry? No. Have you used it with the Sandbox, the old App Engine?
No.
Have you tried? Because it could possibly work. Maybe we'll talk about it later.
Yeah.
Yeah, okay.
Okay, and about Kubernetes and load balancer. Is it possibility to configure load balancer that by default it will not spawn any instance? And
I can't hear you, Valentine. Sorry.
Hey. So the question is it possible to configure load balancer of Kubernetes in such way that it will not spawn any instance and only spawn on a request?
You mean auto-scaling?
Yeah.
So no, there's not auto-scaling currently. Auto-scaling is quite a difficult problem. So with Kubernetes, what we need to be able to do is scale our pods so that we can have more pods to service the incoming traffic. But when we scale the pods, we need to also be able to potentially scale the nodes. So we may have to resize our cluster as well. So it's very important that Kubernetes understands how to scale, but doesn't actually do the scaling itself, because it has to rely on the underlying infrastructure to do it for it.
Okay, and the last question about the very nice UI of Kubernetes. Why it's not shipped by default in even Google Cloud Platform? You need to install this additionally visualizer of Kubernetes.
This visualizer?
Yes.
Yeah, so
for me, it was quite hard in the first time to install it on my project.
Right. So basically the question is, when will we have a visualizer for Kubernetes? Is that correct? Yeah, so I think it's going to happen fairly soon, because we have the user interface currently, which has the performance settings, CPU and memory for each node. It shows you where the pods are deployed to, but we don't have this kind of visualization. I think there's some interest in making something like this available within the user interface. But again, it's going to be dependent on where you deploy Kubernetes, on Amazon or on Microsoft or on Google or on Mesosphere. Where does the UI come in? Is it going to be built into the Kubernetes runtime, maybe as a pod or part of Kube UI? That's always possible, but the best way to find out is probably to go onto the GitHub repo and look at the issues that are being discussed there. Okay? Cool. And just to quickly mention as well, Kubernetes status. Kubernetes is open source. You can go to various different places to find out more, and also we want your help in contributing to Kubernetes. The same with gRPC too. We have many, many links, and ultimately the slides are here. So if you copy that link, you go to the slides, you'll be able to get all of the information that we've been talking about today. Yeah, I'm sorry we ran out of time. I thought we had 40 minutes, not 35.
Yeah, just one another question.
Hi.
Yeah.
Is it okay to extend the gRPC client class?
Sorry, what was the first part of the question?
To extend.
I'm sorry, I can't hear. I'm really struggling.
Is it okay to extend gRPC class, as I understand?
C++?
No, gRPC class to extend it, right?
I can't hear. I'm sorry. Just so much echo. Right, I'm going to go and answer the question in person. Yeah. Hey, sorry, what was the question?
The question is if there is some code generated by RPC with some classes, is it possible to extend it at some additional functionality?
Yeah, definitely, yeah. So basically you get a library that you can build your applications around. So basically the gRPC libraries in different languages provide all of the functionality for you as an application developer to develop your applications for. So it's like a client library. You have the server-side stubs and such like, and the client-side code that you can write your applications to. So yeah, it's very easy to extend. That make sense? Does that answer your question? Okay, cool.
Okay, thanks, Mandy. It was interesting for us, I think. And so we have, again, a break for 10 minutes. See you after them.
Thanks.
Thank you again.